in the previous lecture, we were at this state. We were understand this height.txt, the data set typed by E.S. Pearson, and we're trying to understand what relationship is. And we thought it should be like this, but avoid is there something going on with these ranges and the outside people and so on and so forth. Please sort of split the data set into 3 parts. We round off the people to 58, 64, and 68, and try to see how the data set behaved in these verticals, and we try to understand this thing. Now, before I go into working with this data set, what I want to do now is, one second. Before I start working with this data set, what I want to do now is, I want to just go to basics of linear models and come back and work with it. So first I'll work with some similar data set. And once I work with the similar data set, I'll try and see how to sort of fix a relationship in this particular data set. Okay. So now I want to just give you a brief idea of just some preliminaries on modeling before I sort of do this whole exercise on the data set of heights. So what we'll do is we'll now work with some similar data sets. So what we'll do now is we'll develop techniques. Okay, I'll just say develop a technique to use, I'll just call it a linear model. So again, why I'm using linear model will come to as I go along with this course. Is linear model valid for the data set? Also the question they want us to understand, but I will not understand that today. I'll understand that as I go along with this course. So now, so what does this mean? That means I have my data set xi and yi, 1 less than equal to I, let's say there are n points. That's my data set. And what do I mean by linear model? By linear model, I mean I want to find, let's say, A1 and A2 such that y equal to A1, A2x plus A1 is a good approximation. This is what I want to do. Okay, so I haven't told you why this is the case and why I want to study this particular thing, but this is one set of models that I want to understand in terms of the model specific. Right? Of course, there could be other models in the market that one can work with, but I'm not going to do that. I'm just going to understand this. Of course, in practice. So in practice, when you do some study like this, you should also keep in mind how the model is going to be used, right? So what are the questions that people want to understand? So that's something you must understand. So you must keep in mind what are the hypotheses one wants to test. For the data. So you must keep this in mind while doing this, right? The other thing is that if you don't want to do statistics, let's say you want to do only sort of brute force understanding of when is this how do you find A1, A2? That's a good approximation. In some brute force way you want to do this. Then some people, what they do is they will split the data set into 3 parts. So one is called the training part. They will use the training part to sort of understand how to explore and how to find this A1 and A2. That's the training part. The second part, what they'll do is they will have a buffer part, which is what's called, I'll call it the query part. So what you do is, let's say in the training part, let's say you don't get a unique answer. You get 1 or 2 models. You get 1 or 2 models in the training part that you think are quite good for the data set. Then you use it to see which works better in the query set, the query part, which works better. And then the last one is you go to a test data set and see how the data is performing. you evaluate performance. Once you make a choice, you evaluate performance. So this is typically one naive way of sort of, or one accepted way in, let's say, in many machine learning and data science courses to do this sort of approach. You take a particular model, use a training data set to understand the best A1, A2, and then that's how you run with it. And you can split it into many, many parts. So typically people use a split like, I think 60% of the data set, they'll use it for training, and another 20% for querying, and then another 20% for testing. I hope I got the math right. That's 60, 20, 20 is 100. Very good. So, but of course, you must not change train to query, and you can't change the model after you go to query. So it's very important to keep exploration separate, fitting separate, and prediction separate. Is very, very important. You can't mix the data sets. So now I'd like to sort of tell you, so how does one do this? So there's really no good way to find A1, A2. I just think find A1, A2, right? So what will be your measure? Right? So what I'll do is, let me go to the R code right here. So let me go to the R code right here. So in this R code, I'm going to use a package called model R. So please load it up if you don't have it. I'll wait for a second. Load up. And this option in A action is no harm. It's just sort of you can ignore it. You can use it if you want. Don't use it. So, but then a sim1 is a data set in the package model. Let me write this down. So we'll use this package called. Let me just use the same template. How to add a template? Let's see. Current template. We'll add one. Okay. So what we'll do is we'll try to work with simulated data set. It's from a package called Model R. Model R that I'll use. Okay. That I'll use. Okay, that's the package. So install it if you don't have install it, and the data set that we use is called sim1. So sim1 is the data set we will use. Is the data set that we use. So what I do first thing is I just go and scatter plot sim1. Okay, so sim1, you can just scatter plot. So it just scatter plot of this data set. So you can look at, you can do many things. You can just look at end row sim1. It'll tell you how many points there are. So end row sim1 tells you there are 30 points, and the scatter plot gives you this X and Y across this thing. And you can even check head of sim1. You can check and then tell you what the points are like. So one thing you notice immediately is that same X, 3 Y, and you see this. So let me go back to my slides. So we notice if we just plot the thing, of course, this then in the PDF file, they're sort of simple. One is that you notice that this data set called sim1. Okay. And the first thing you notice is that each value of X, there are multiple values of Y. It's not a unique code. It's like sort of, so one is that at X equal to 1, there are 3 values of Y. It's 1, 2, and 3. And similarly, so on and so forth. Okay. So we just plotted them to see how it looks. So now, of course, now what all can be observed? So the first thing you observe is there is a pattern, right? There is a pattern. So I don't know how to tell you how to do it. You can observe that there is a pattern. That's the first observation, right? This, you can see that it's kind of growing like this, right? That's the first thing you observe. But of course, now let's say we think that we sort of conjecture now that the pattern is linear. Okay, so we conjecture that it's a linear relationship. So I want to try to understand a linear model for this data set sim1. Okay, sim1 data set. And I conjecture the linear relationship. So now I have to find the linear relationship. So what I'm going to do next is I do this little, so I don't know which line is thing. I have no idea how to choose the line. So let's do a little, let's say we have no statistics. We only have a computer in our hand. So let's go to the data set. So what I do is I first generate 250 uniform numbers between -20 and 40, and 250 uniform numbers between -5 and 5. So the slope is between -5 and 5, and the intercept between -20 and 40. Okay, I generate 250 numbers. You'll all generate them. I'll generate them. So you'll get different from me, but get that. Then what I do is, I don't know why I repeated the command here. I'm not sure. Let me delete this. Okay. What I do is I create a data frame with the slope and intercept that I have. A1 is intercept and A2 is slope. I take my ggplot. I make a frame for the data set. Then all I do is I draw all these lines for all these slopes. Okay, and I thin them with alpha equal. I just thin the line a little bit. And I add the scatter plot as well. Let me just do that now. So let me do that. So now I should get lots of lines. I should get 250 lines. So you should get 250 lines. You see that? So some are good, some are bad. No, like just like very bizarre, right? The whole thing very bizarre. So let me go back to the file. So what have we done here? We have taken 250 uniform chosen variables. So A1, which represents the intercept. So we took 250 people uniformly between what number? Let me check the number between -20 and 40. So in the interval -20 to 40. So that's where the intercept was, right? So uniformly chosen. So that's not properly, so it's clear. So A1 intercept uniformly chosen. Random variables in blah blah, and I took 250 of them. I took 250 of them. And what is the slope I did? The slope is A2 is the slope. Right? That again I took 250. Let me go and see what I took. I took between -5 and 5. Right? So let me just copy this down. So A50 I put chosen in -5 and 5. Very good. That's why, right? And then I plot the lines. I just plotted all. So here, what we did, we just plotted all the lines. Plotted 250 lines. And the data set. Now, if you look at this picture, you don't know which is the best line. Everybody's going haywire. You think there should be a line that goes like this, but at least if I choose random lines and I just plot them, there is no sort of things. There are 250 models on this on this thing. So one thing to think about is that on this page, I've produced for you 250 models, right? 250 linear models. Right. So most of them are very bad. Some of them seem to be good, but you have to go and find maybe this. You go check slowly. Maybe this line seems to be okay. This line seems to be okay. But of course, there is data set in some sense. How do you understand which is a good line and which is not a good line? Right? That's one thing you should do. Let me go back to the. So now let me go back to the R code again. Let me try to see if I can convince you that there is a way to do this. So here I just take what I do. First thing is I just take any number between 1 and 250. The sample command just chooses 1 and 150. I take any line. So let's say I take the line. So here the line, what line I picked? I picked the 37th line. And then I just plot the 30. So here I plotted the 37th line. That's the line that goes down. You may get a different number when you plot the line. Get a picture that goes down there. And I plotted these red things. Right? So then let me go to a PDF file. What did I get? So a PDF file that is in my slides. What line did I plot? Let's see. Let me go over. I plot the 130th line and it went up with this. Okay. So what is happening here in this line? So what am I doing? Two things. I have in the code, I have plotted plotted straight line, geometry line, right? With slope A2 of the number and A1 is the slope of the intercept of the line. And I've plotted the points for the data set. And then this, what I've done is I have drawn a line to the data point. That's all I've done, right? That's all. So for the 3 lines here, you can only see 1 line, but I've drawn 3. I'm not jittered them to sort of show you the lines, but I've drawn these 3 lines. Right? That's all I've done. So let me go back to let me explain. So what have I done? I've chosen this particular chosen. I've chosen the 1/30th line in my graph. I plotted the line. And then these people right here, the red people right here, are essentially the distance. The distance of the point from the line, or the distance of the points from the line. That's all. So they're called residuals. Come to that as we go along in the class, but we'll try to understand how to do this. So one way to understand how a good line is that we should minimize all these red distances. They should be, maybe I should move this line from here. Maybe I should take this line and then move it somewhere here. It might minimize all the red guys in some sense, right? One way we should. Again, so one criteria could be to minimize the distance. Of course, so one criteria could be to find a good model. So to minimize is to minimize the distance. So some people might say sum of distances. But this is now prone to cancellation. So you might get a sum to be 0, but there may be large negative and large positive. So you may not want to do that. Someone come and say, don't do this. Do something like you minimize not the sum of distances, but the absolute value of sum of absolute values. So let's see if I can done sum of absolute distance. Someone will come and say that. That's again, it's also okay. But then finally, what we do is I'll try and show you the best thing to do is not the first 2, which is probably this thing, which is a little harder. If you want in calculus, what you do is you minimize the sum of distance squared. That's what you take. Finally, has to do. So this is something you should not do because it's prone to cancellation. And the first one, the second one is a little bit hard to solve, so you can't do this. But the third one you can do. So maybe in the 3rd or 4th week of the course, I'll give a lecture on how this history came into doing these to come to this particular square problem. So this is not good because it's prone to cancellation. This is okay, but it's too hard to do. So this is quite hard to do. It's doable, but it's hard to find an optimal problem. And this is what is called the least squares approximation. So we'll come to this terminology as we go along the class. Today, just feel for what's going on. That's what we're going to do. Okay. So now to do this, I have to write an R code to understand this. So what I have to do, first, every line, I have to find this quantity, right? Then I have to find the minimum over all possible lines available for you, not from my 250 model, but from all possible models, and try to find the answer for them. Right? That's what I have to do. So let me try and go back and check, show this R code a little bit. So let's go what the R code is doing. Come back and work with it. So now here, what's happening is that now what have I done here? So now I've already shown you what's happening in this first part. The second part, I'm defining what the line is. That's what the model part is. It's defining what the line is. Okay, I'll do the model part. Okay, defining what the line is. The second one, what it's doing is it's measuring the distance from the line to the points. Okay, so what it does is it takes the difference between the data point and the line. It takes the square of this, and the average of this is the total distance the mean difference squared it takes, and then it measures the total distance. This thing will give you a number for that line, for the 30th line, it gives you a number 31.2. And then what this command does is, this is an optim command, which is a minimizing command. It's like a computer version of calculus. To give a calculus problem, it will minimize, it will find where the derivative is 0 and find the value of the minimum. So what it does is, it's called optim, it's called a short form of optimize. So what it does is, it starts from 0, 0, and then it takes the distance function, and then it minimizes the first coordinate. The first coordinate is the slope and intercept. That's what it's going to find. It's a two-way problem to solve. And the data set is sim1. That's one we have as data frame. If we do that, it tells you, if you come down and run it down, it'll tell you that the best intercept is 2.2248 and the best slope is 2.01. That's what's going on. So let me now go and then you can also see what the distance at that point is. That distance is 2.12. Right? And should compare the distance at the line that we had was 31. It's quite large, right? That's what we had. Okay. Now let me go back to my thing and explain to you what's going on here, both mathematical terms and. So what do I do now? So what am I going to do now is that I have my data point. Right? Data points to what? Data points are xi, yi. Right? It's 1 less than equal to y less than equal to. That's my data set. Then what I do is I think of it as a, let's say, call this the measure distance. It's down. This thing, let me call this. I measure the distance of my favorite line, right? So line has only two properties, right? It has a slope and intercept. Intercept is a1 and slope is a2, right? So now what will happen? My data point is y1. So let me make this in orange. So the function of orange. Let's say holding on orange. So my data point is y1 xi. So what I'm going to do, I'm going to take my yi. I'm going to see how far it is from a1 plus a2 times xi. That's where the line is going to pass, right? And yi is my data point. So this will tell me the true distance between the line and the data point. And then what am I going to do? I want the mean square. So what I'll do is I'll first square it. So I'll first square the distance, right? Then I'll take the average. That means I'll take 1 over n, that n points are there, and I'll sum from I equal to 1 to n. So for every line, I do this. That's what I do. So I just take the sum of distances from the line. So that's exactly what I'm doing. I'm going to take these people, for each person. That's what I'm doing here, and I'm going to square it. I'm going to take the average of the total distance of the square. Okay. That's exactly what's happening here. I'm generating the line. I'm taking the difference. I'm taking the square root of the mean difference. I'll take a square root of the mean. I'll take a square root. So I go here. I do this. Of course, you don't have to take square root. You can take the square of this. It's minimizing the same idea, but let's just do this. And then I use the optimum function to minimize this function, the function of a2. Then what I do is I solve this problem. I find, purple. I find the minima a1, a2. I'll just find the a1 and a2 that minimizes. I'll just copy this guy and I'll put it down. Sorry. Very quickly. Once you do this, then you know exactly the answer. The R, you can do it by hand if you want. If you can do calculus and do it, but R has an optimum function. You can use that function to do it. It finds the best intercept is 4.22 and the best slope is 2. So then you can go and plot it. So let's go and plot the line. So plot line. Let's go first thing. Let's plot the line. So I discover just plot the line. And I just get the line like this. So the line is going through most of the points, and these are the residual errors that you have. Right? So in my slide also, I've got a different weighted color, but the same idea again. So this is plotted. The line. What properties it have? Intercept is 4.22 approximately, and slope is 2.05. So it's within our range of uniforms. So the line would have been there in that sense, somewhere, and that collection will be started off with. But this is the best line under this criteria of minimizing. So you arrange this properly, plot to the line, intercept is this, and slope. And you can see this line also has errors, but it seems to provide a good approximation. So it seems to provide a good approximation. Very nice. So there are in this course, we will, as we go along, we will study various things. So one is that we will study many things. How to judge the fit, or how to judge the model. So we'll understand that. So in many ways, for example, is the linear relationship the correct relationship? Is something else going on? Right? And once we have the model, if the model characteristic is a linear model, is the line the correct fit? Is this the best line? Is this the best possible solution under the model? Like, are we doing the correct thing? So I should say, is this the best possible solution? That's kind of the goal of the course, and how to understand this better and better. If you have assumptions or data set, can I give you better and better understanding of how the errors behave and how the model behaves?